Hello, good afternoon to everybody here in Europe. It's a pleasure to welcome you here for this new installment of the MixGen series. This is the 8th event that we have in this second season, where we address different topics of simulation and modeling, bringing together more experienced and less experienced researchers, but always young at heart, to have the possibility to learn about different methods and approaches, computational approaches to the challenges in the different areas that are associated to the communities at CCAM, and also to have presentations by younger people, and also have a place, a moment for an informal interaction, which is also close in spirit to what we always pursue at CCAM. So today's session will be about electronic energies beyond density functional theory, and it's a pleasure to have with us Lucia Reining from the École Polytechnique and Jean-Baptiste Van Kamp from the University of Yaoundé as the younger presenter today with us. As usual, we have this first part with these presentations, and then there is the second part in Gather, for those of you who have registered, that allows for informal presentations, interactions, and also poster presentations. Today, we do not have many posters, so the second part will be mostly a place, a space where everybody, all of you, can interact and discuss scientifically and build on the presentations we will be listening. Now, before we move on to the scientific program, as usual, I always like to give you a couple of pieces of information. One is about how we should interact and behave on these online events. I think that by now we are quite used to them, but just as a small reminder, the meeting is recorded. This first part is recorded, and then it will be later available on the CCAM YouTube channel, so you can come back to the presentations if you want, or if you don't have the time or the opportunity to attend the whole event today. For all the participants, the video and the mic are in principle not active, and also the chat is deactivated in such a way that all the interaction between you and us and the lecturers today will take place through the chat feature of the Q&A feature of Zoom. For the first presentation, for Lucia's presentation that is longer, you can, during her presentation, you can write down if you have questions, and then I will relay the questions to Lucia, so she doesn't have to worry about the chat, the Q&A channel. And then once she finishes, then we will have a more extended moment for having questions and discussions. And again, in that case there, it's enough that in the Q&A channel of Zoom, you simply indicate you want to ask a question, and then we will unmute you, so then you can directly ask the question. I think it provides a more direct contact, and then also if the question is rich enough or if the answer does not completely satisfy you, you can build on it and enter in more in a dialogue with the presenters. In the case of Jean-Baptiste, because he has a shorter presentation, I will not take questions during his presentation, but then after that, then there will be again the time for discussions using again the Q&A channel. And then one last piece of information for this MixGen season, the second season, there is one remaining installment. This will take place next month. So this will be the 7th of July, again at the same time, 3 p.m. in Central European time. And this will be a session devoted to simulating quantum materials. And in this case, the more experienced researcher will be Antoine Georges, also from École Polytechnique, who will be talking about simulating quantum materials. Now, after these presentations, these introductory pieces of information, now we move on to the first presentation by Lucia Reining from École Polytechnique. So Lucia, please, now the floor is yours.
Thank you very much. Let me share my screen. Up and okay, is that fine?
Yes, I see that correctly.
Okay, very good. So I'm really happy to be here and give this introductory talk. It's about strategies to deal with the many-body problem in materials. And the first word is strategies. And so it's really what I would like to convey is our way of thinking and approaching this problem, of which we know that we cannot solve it exactly. We will never be able to solve it exactly. And the things I will be saying are illustrated with applications. And so there are several people who have contributed to the work in this talk. And in particular, Ayub, Matteo, Vitali, Jaco, Martin, Francisco, Marcos, Kai, and all our friends in the group or outside the group. So we are the theoretical spectroscopy group in Palaiseau. And theoretical spectroscopy means that we are, roughly speaking, interested in electronic excitations and everything they can cause, like colors of materials. They can give rise to applications such as photovoltaics, optoelectronics, and of course, much more. And the way we approach this problem, which is a many-body problem because it consists of all the electrons and all the nuclei of this material. And let me say immediately that we are focusing on the electrons, but of course you can generalize, is not by solving the full many-body Schrödinger equation. And therefore, I will take you from the idea of solving a Schrödinger equation and using the wave functions to calculate observables to functionals of other things, and in particular, density functional theory as a background to move on to the main topic, which is Green's functions functional theory. I will take quite some time to introduce density functional theory because we want to compare. And so I think it's important that we have a common terminology and a common basis. And then concerning Green's functions, I will in particular look at Exatons with you, just because it's a very nice illustration. And this will bring us to the fact that the many-body perturbation theory that we are mostly using has its limits and that we have to look for other strategies. And I will conclude with a little ode on models. Concerning this last part, the approximation strategies other than perturbation theory and the models, this depends a little bit on how much time we will discuss and how much time we will have, and we can see in what you are interested. So let's start from our many-body Schrödinger equation, which gives us in principle all the information about the system. So what we want is to calculate observables, which I call O, and the observables are of course given by some operator, which can be an external potential or other for the kinetic energy operator or whatsoever. And then we take expectation values with a many-body wave function, and this is a huge integral, but it's a very simple equation, as you can see. It's a well-known simple equation. So we write the observable in terms of a many-body wave function. And this means that it's a functional of the many-body wave function. If you give me, for example, the ground state many-body wave function, then I can calculate you, in principle, an observable in the ground state. Of course, this is very hard. We cannot calculate the many-body wave function exactly. We cannot store it. So we could also say, do I really need it? Because in principle, my system, once we accept that the kinetic energy is universal and that the Coulomb interaction is universal, is just specified by its external potential, which is a simple one-body operator. And indeed, one could, in principle, also formulate observables in terms of the external potential. This is another functional, but it would give you the same observable. And then, of course, you just have to know how many electrons you have or where the chemical potential is with respect to this potential. You can even write down an expression. For example, this is the finite temperature expression where beta is the inverse temperature. And you see, you have to trace over an exponential of operators, and this is an explicit expression. It looks simple, but it's super complicated to evaluate, and we usually don't do this either. But here we have two possible strategies. One is we write down a simple integral of a function, the many-body wave function, that is damned complicated. Or we use a simple function, the external potential, but then we have to evaluate something that looks simple, but that is actually very complex and exponential of operators. So we have a very complex functional. And of course, we could think that since both have their drawbacks, that maybe we could sort of optimize the strategy and write functionals of even other things that could make our life easier. And of course, you all know density functional theory. So in density functional theory, we say, okay, in principle, my system is well described by its many-body wave functions. I don't want to use them. It's also well described by its external potential. This gives me an expression that I don't know how to handle either. But then comes density functional theory and Hohenberg and Kohn, and they say the system is also well described, completely described by its density, by its electronic charge density, which is also a very simple one-body object. And so, for example, if you want to calculate the expectation value of a one-body operator, which I called O1, well, this also is very simple. You have the one-body density, so the charge density, which is local in each point, and you just have to calculate this integral. And density functional theory tells you more than that. It tells you that not only for the one-body operators, but actually all observables in the ground state that you could imagine, there must be such a functional. Suppose we have the functional, then we need the density. That's not so obvious, right? Because in the case of the external potential, we know the external potential if we know our system, but still we don't know the density. We know in principle how to calculate the electronic density. It's an expectation value in the many-body ground state. And these here are field operators that create and annihilate a particle. So we know the expression for the density. But again, since we don't want to calculate the wave functions, this is not what we want to use. So we don't want to calculate the wave function. But here comes the next good idea in the context of DFT, namely the variational principle applied to this case. We know that the energy, the total energy as a functional of the density takes its minimum at the true ground state density. So if we know how the energy depends on the density, we can minimize this and we find our density. The problem is we don't know how the energy depends on the density. So we need a next great idea in DFT. And this is that we can actually build an auxiliary system, a simpler system, a non-interacting system that yields the same correct density. We don't have to solve a many-body system to get the density. So this system is the Kunsham auxiliary system. It is a one-body Schrödinger equation where you have kinetic energy and an effective potential, and this consists of the external potential, the classical electrostatic potential, which is the Hartree potential, and the rest, which is called the exchange correlation potential. Okay, so this is a much simpler system, and then you can use the one body, the one electron wave functions to construct the density as usual in a non-interacting system. But you have to be careful. This system is designed and its potential is designed such that it yields the correct density. It doesn't yield anything else correctly. And this is like building a simulation chamber, which you do many times in physics. For example, you want to simulate a material in zero gravity. You can fly out in the space and measure your zero gravity and get a lot of answers about what happens why out in the space. For example, if there's a little green woman living out there, or you can build this simulation chamber for zero gravity, then you get the answer how your material behaves in zero gravity, but you will not know whether there is out in space a little green woman. So the auxiliary system answers less questions correctly. And this is why it can be simpler, of course. And then we have another problem here, which is that in this potential, we know the external potential, we know the Hartree potential, but we do not know the rest, which is called the exchange correlation potential. And you can imagine there is a link to the variational principle, which also gives you the density correctly. Indeed, this exchange correlation potential is the variation of the exchange correlation energy, the contribution of exchange and correlation to the total energy, which we do not know. So we don't know this potential either. And then we need the next great idea in DFT. And this is how actually DFT, I think, could be so successful, namely that since we are not able to determine this auxiliary potential in our material, we take it from a model. And the easiest thing to do this is the local density approximation. So this is still in the work of Kunsham. It's an approximation strategy. We have this exchange correlation potential that we don't know. The only thing we know, it's determined by the density, because it's the density that describes our system in density functional theory. And we say that we can take this potential from the homogeneous electron gas, which is a much simpler system. It's a simple system with a homogeneous density. And in this system, people have been able to do calculations, and in particular, quantum Monte Carlo calculations, to get this number. And the only question is then, which density do we give to this homogeneous system? And the answer of Kunsham was to say, we take the local density. So we calculate our gas for every point where we want to replace this real potential. At every point, we take the density that the system has in that point, we make it homogeneous, and we take VXC from there. So we use a model to simulate the real system. And we do this in every point. In every point, we use a different model. And this is based on the insight of Walter Kohn of nearsightedness. Physics is nearsighted. If we want to calculate a material, we just calculate maybe a little piece of it or a big chunk, but we never calculate the whole universe, because at some stage it's too far away, it doesn't contribute. And the idea of Walter Kohn was that this problem is extremely nearsighted. So if we are in a given point, all the rest we don't care about it. It's just the density in that point that matters. So we can picture it like this, the local density approximation. We have a series of homogeneous electron gases for which we can calculate our exchange correlation potential. In the real material, at every point, we look at the density and we take the result from the corresponding electron gas. This is absolutely great, because the electron gas was calculated essentially once and forever by Sepaly and Alder. The result has been stored or interpolated, and it has been shared with all of us. So every time we calculate for a given material exchange correlation effects, we actually take the calculation that has already been done by Sepaly and Alder many years ago. That is so efficient. If we think about it, it's really amazing. So, okay. So let's say we have a good approximation for our exchange correlation potential. We can get the density. So now we could evaluate this functional. The problem is we don't know the functional. For most observables, we don't know the functional. I had written you the functional, how to calculate the expectation value of a one-body operator. This we know, but the other things we don't know. And so what shall we do if we don't know the functional? For some things, there are approximations. For example, the exchange correlation total energy, the total energy. But very often, when we don't know, we use the Kunsham system. We use our auxiliary system, our fake world, the fake world that we have designed to get the density. We use it to calculate also the other observables we are interested in. That means that we actually asked for the little green woman, although we know that this system will probably not give us the right answer. But to be less nasty, we could also say that we can see this as an approximate functional. So it's the best sort of functional that we can imagine is to calculate our observable in this auxiliary system. Now, what does this give if we are interested in spectroscopy? Because this is the kind of observables we're interested in, spectroscopy. For example, photoemission. Okay, in photoemission, you come in with a photon here, and then you kick out electrons from your sample, and you have an analyzer, and you measure the kinetic energy of these electrons. And this gives you information about the energy that you think these electrons had in the material. And you can also measure the angle, then you get angle-resolved photoemission. And when you do angle-resolved photoemission, you can depict this as a band structure. So for every angle and every kinetic energy that you measure, you get a point in your band structure plot. This is, of course, a single electron picture. We will come back to this point later. So you do this band structure plot, and this means that every time you measure, you get a peak. And this peak at some momentum, here's momentum, and at some energy, here's the energy axis. And in the single electron picture, every electron carries its energy, and so you get a series of peaks, which gives you the band structure. Okay. So what's the result? Here's an old calculation by Michael Rolfing and co-workers for bulk germanium. This is just a very typical thing. So you have the experimental result here in the right panel. You have the experimental dots, and you can see germanium is a semiconductor. In fact, the gap is here. And on the left side, you have a calculation that has been done using the Kunsham system and the Kunsham energies. So the energies, the eigenvalues of the Kunsham equation to replace the true band structure, because it's the best we can do. And on top of this, so on top of having used the auxiliary system for a sort of not allowed purpose, we also made the local density approximation. And as you can see, the result here looks at first sight very similar. It's actually amazing. In particular, the occupied states look very similar. But if you concentrate in the band gap region, then germanium turns out to be a metal in this calculation, whereas it is a semiconductor in reality. And this is this famous Kunsham band gap problem. So now you could say, okay, but you did two approximations. I mean, one, you used the Kunsham system. Second, you used the local density approximation. How can I know that it's not all the fault of the LDA? And in fact, people very often say it's because we did LDA. Okay, it has long been advocated that actually the main responsible is the Kunsham, the wrong use of the Kunsham system. And I put you a series of references here of people who have been working on this. They did a lot of approximations to discuss this and came to similar conclusions. What is new here on this slide is a recent work by Ayub, Matteo, Siwan Chen, and Shiwei Zhang, and myself. So we got a very, very good charge density for semiconductors and insulators from the auxiliary field quantum Monte Carlo calculations of Siwan and Shiwei. And Ayub has inverted the Kunsham equation to reconstruct the exchange correlation potential. And from this, the band gap of this exchange correlation potential, that should be in principle the exact Kunsham band gap if we think that the density of the quantum Monte Carlo calculation is close to exact. And the results you can find here for silicon and sodium chloride, and compared to the experimental band gap down here. And you can see that in all cases, this gap that comes from the Monte Carlo calculation is much smaller than the experimental gap. See, the LDA gap is even smaller, but the biggest error really comes from the use of the Kunsham system itself, even if you do exact Kunsham. And this holds for silicon and sodium chloride. By the way, the PBE calculation turns out to be actually quite close to the exact Kunsham in these cases. So no doubt, the use of even exact Kunsham doesn't give you the good photoemission spectra, in particular the good photoemission band gap. Okay, so let's conclude on this density functional part before we move on to the Green's function. So density functional theory is definitely a great idea. And as I have shown you, there are a series of great ideas actually to make it usable. And one of these is the use of an auxiliary system to get the input, which is the density. We first have to find it. And to have this auxiliary system, we have to design the auxiliary exchange correlation potential. And one of the strategies, it's of course not the only one, but a really very, very powerful strategy is to take this potential from a simpler system. And we can do this in an easy way using the idea of nearsightedness. And this leads to the local density approximation that is not that bad after all, in many cases. But then we don't know the functionals for most of the observables we're interested in. And so we take them from the auxiliary system, although we know that we shouldn't do it. And this gives approximations that are actually, in some cases, very rough. Okay, so as I said, this can be seen as an approximate functional. And the question is, what are the observables we are interested in? Now we come a little bit more in detail to this. So we're interested in spectroscopy. That means we shine light or some perturbation on a system, and the system reacts to this perturbation, makes a transition from the ground state to some excited state. And what we need here are the wave functions of the ground state here, psi, and of the excited state, which I labeled S. And then to go there, we of course have some operator, for example, a dipole operator, maybe some frequency. Okay, so this is a typical ingredient that we need, this kind of transition amplitudes. Okay, from this we can get the phase factor out of the wave function. So this gives us energy differences, and if we Fourier transform, it gives us poles at excitations energies, and we have this transition amplitudes that are integrals of the many-body wave function. So it's clear that you don't know how to write this as a functional of the density. But these are the ingredients that we need. And this brings us actually to Green's functions functional theory. So we say we don't know how to express all that stuff in terms of the density, but we know what we need. And we can take these ingredients and build objects with these ingredients that are really suitable to describe the observables we're interested in. In particular, we can build what we call the one-body Green's function. The one-body Green's function, which I call here GT, because it's a time-ordered version, okay, consists of the amplitudes, these transition amplitudes. So it's not exactly these ones. These ones are for neutral excitations. Here we add or subtract particles, but it's the very same principle. And it has energy differences here, so the Fourier transform of these phase factors. And this E lambda is actually the difference between a system where I have added a particle, so n plus 1, and the ground state at n electrons, or a system where I have subtracted a particle, so n minus 1, and the ground state. And in both cases, I can be, when I add or subtract a particle, I can end up in an excited state labeled lambda. So the one-body Green's function is simply the sum of all these possibilities, all these transition amplitudes and their energies. And the good thing is, you see, if you take the imaginary part of this object, and actually of the diagonal of this object, for example, in K space or in some basis, okay, if you take the imaginary part of such an inverse so 1 over x with some little small imaginary part here is just a delta function. So this gives you the sum over all possible excitations, which are delta functions. At each possible energy, there's a delta function and its amplitude. And this is what we call a spectral function. And this is the kind of thing we measure in spectroscopy. In spectroscopy, we measure, can the system absorb a photon and go to this energy? And what is the probability that it will do so? So you see that this spectral function is a very simple expression if you have the one-body Green's function. And it contains actually a lot more than what we have in the simple single electron picture. In the simple single electron picture that we had before, we have an energy for every electron. Now, we, for example, if we do photoemission, take out an electron, this leaves a hole behind. It's a perturbation to the system. The system, when we do this, it can be excited. So it can, for example, oscillate and make plasmons. And this takes energy, this excitation takes energy. And so the outgoing photoelectron has less energy. And so we find extra structures here in the spectrum that are called satellites. And also the main peaks, which we call quasi-particle peaks, can have some broadening because there's a decay in other excitations. Everything's coupled. There can be a renormalization of energies. So the spectrum can look very different from this single particle spectrum. And again, you can imagine that you will never ever be able to get such a thing out of a Kunsham system. It's just not possible. A Kunsham system will always give you a series of isolated single peaks. But this is contained in the true spectral function that is the imaginary part of the one-body Green's function. Okay, and this is really what you measure. This is, for example, a very simple system, bulk aluminum, so no suspicion of strong correlation, at least not here. And it's an experiment at the Swiss light source. And you can see up here, so this is the K space here, from L to gamma to L. And you have the bands. So this is what you get when you do band structure calculation, just the red stuff here. And then you have a lot of additional stuff. That's the color code, right? A lot of additional stuff, and in particular, the first satellite, the second satellite, and the third satellite. And these are plasmon excitations of aluminum. If you know the energy, you can just check that this is a plasmon excitation. So that's really very important when you want to look at experimental spectra. Okay, so we have a really simple way to get, we have a very simple functional, let's say, of the observables we are interested in as functional of the one-body Green's function, whereas we didn't know how to write this observable in terms of the density. Super. So comes only the last question, where do we get the Green's function from? Like in the case of the density, where do we get the density from, right? So in the case of the density, we had this auxiliary system, very simple. Now we have more requests. We want to get a more complicated object. The one-body Green's function is more complicated than the density. So we need a more advanced simulation chamber. And in fact, our more advanced simulation chamber is an equation that looks very similar. You can formulate it in these terms. So you have kinetic energy, external potential, Hartree potential, like in the case of Kunsham, but you have now a more complicated potential-like object, which we call a self-energy. And this self-energy is non-local in space, like a Fock operator. And it is frequency dependent because we have all these processes that happen in time in spectroscopy. So everything's frequency dependent. And this means that the system is much more complicated. And usually, actually, we don't write it like that. Usually, we write it in terms of a Dyson equation, where you have the Green's function you are looking for, the non-interacting Green's function that you know how to write down, the Hartree potential, and this exchange correlation self-energy. Okay, and this is the self-energy, and this frequency-dependent self-energy is responsible for all these extra effects that we have just been discussing. Okay, but we don't know the exchange correlation self-energy. Like in the Kunsham case, we don't know the exchange correlation potential. Okay, in the Kunsham case, our way out was the local density approximation, nearsightedness, locality. What shall we do here? Can we do a local density approximation to the exchange correlation self-energy? It's tricky, right? Because it depends on two places in space that can be actually quite far away. There are attempts to work on this, for example, the work by Wang and Pickett. But you could also say, no, but I am working here with Green's functions. Can we do a local Green's function approximation? We will come back to this later, but as you see, if you just look at it, it's not obvious to define locality in such a system. So we go another way, and that is the way that is actually probably the most used way today, which is perturbation theory. Completely different strategy. Okay, so we have our one-body Green's function. The one-body Green's function can be written like this. So you have your n-body ground state. You add a particle with a field operator. This is a creator in some point in space and time. And then this propagates, and you look at the probability to find it at some other point in space and some other time. So it's a propagator, and we depict this by Feynman diagrams by just an arrow. This is a propagation of a particle. And perturbation theory expands the result in terms of what happens in the system. It's a sort of story writing. So you have a non-interacting particle, it propagates, it has a Coulomb interaction with all the others, and this is the density of all the others. So this is the Hartree term. Hartree term modifies your propagation. Then you have exchange. Particles are not distinguishable. So you can exchange Green's function lines, you can exchange arrows, and this yields the Fock diagram, the Fock operator. And then you have many more things that can happen. You can propagate, you have a Coulomb interaction. This is repulsive for the other electrons. So an electron will move away, it will create a hole where it was, and a new particle where it now goes. That's an electron hole pair. And you can see here an electron hole pair. That makes a little dipole. It makes a new potential with a Coulomb interaction and modifies your propagation. And many such things and scatterings can happen. And you all sum them up, and that gives you the self-energy. And perturbation theory means that you select the most important processes, the ones that you think are the most important for your problem. And in an extended system, what is very important are these polarization processes we have just been talking about, creation of electron hole pairs that actually modify the Coulomb interaction. You see, it's like an insertion in the Coulomb interaction. It's an effective Coulomb interaction, and you can do this many times, create many of these bubbles. That is screening. It gives rise to a screened Coulomb interaction, and this is why this approximation is called the GW approximation. G is the one-body Green's function. W is the screened Coulomb interaction. If you put the bare Coulomb interaction here, you just have Hartree-Fock. This is a screened Coulomb interaction instead of the bare one. And this is Hedin's GW approximation, which many of us are still using. So screening can be expressed in terms of a frequency-dependent inverse dielectric function. And this is why the self-energy is frequency-dependent here. Okay, so if you compare to Hartree-Fock, in the case of Hartree-Fock, your electron, if it propagates, it will not influence the others. The others are like a rigid system like ice. So you are an ice skater if you are an electron in Hartree-Fock. And in GW, you are more like a boat on the water, because now the water can react to your propagation and can influence your propagation. And actually, Lars Hedin called this an electronic polaron, because you really polarize the medium around you. So that's the essence of GW. And this is what is used in a standard way for band structure calculations today. So we have the example of germanium again with the 0 band gap in LDA and the semiconducting band gap in GW. In Hartree-Fock, you get a much too large band gap because there is no way of the system to react, to relax. And in GW, you have actually the continuous lines here that fit nicely with experiment. So, and you have many, many examples where you see all these plots where all the band gaps are close to the experimental ones. We should say that it's not only band gaps, actually spectra with a little add-on can also look similar. So here I show you the aluminum again. In the middle, you have the experiment. On the left side, it's not just GW. So GW would give you a nice band structure here. It's a GW used in the cumulant way. I don't have the time to go into this, but essentially you build a sort of better auxiliary system that you then treat in perturbation theory on the GW level. And you see you get the first satellite, the second satellite, and so on in the good position. And on the right side, we have simply added other things that happen in the experiment and that I don't have the time to discuss here either, unless you are interested. But we get very nice agreement with experiment on this level of perturbation theory. Okay, so now let's go beyond this and let's move on to exatons, and let's move on to optical absorption. In optical absorption, you don't kick out the electron of the system, you promote it from some occupied to some empty state. And the photon comes in and you measure the intensity that's going on. So you, in this way of promoting electrons, you of course create holes and electrons, you create electron hole pairs, which is a two-body problem. Okay, now we have this auxiliary system that we have just designed, a very sophisticated one, where we get, as we have seen correctly, electron addition and removal, which are one-body properties. So this kind of little green woman we can ask for, but other things are still forbidden. this doesn't give us the answer to all our questions. And in particular, when we have a two-body question, again, this would be too simplistic. If you use it, and if you treat this system of absorption, this problem of absorption, as if you had just your effective electrons from your nice auxiliary system that is designed to give you one particle properties, then you would have a hole that is correctly dressed by your screen-Coulomb interaction and your electron correctly dressed. And then your two-body result, your electron-hole pair, would be just a Green's function for the electron and a Green's function for the hole. And this is called a random phase approximation. And you can see what happens if you apply it. And this is the work of Vitali Gorilov in collaboration with Martin Feneberg, Rüdiger Goldhahn, André Schleife, and Walter Lambrecht and Matteo Gatti. Okay, so this is V2O5. It's a layered oxide. You can see the layers here. Okay, and it has vanadium and oxygen atoms. And this is an absorption spectrum in such a plane. Okay, and the experiment is these red curves here. You have a very prominent peak at the onset, and then the spectrum continues. And if you do such a calculation, so which I've just shown you, just the best electrons you can calculate and the best holes you can calculate in your auxiliary system, you get the orange curve. And you see that it's much too high in energy and the onset has too low intensity. And that's a typical result of such an RPA calculation, because we used the thing, we treated the problem as if we had electrons and holes independently. And of course, you know, electron and hole should interact. And this interaction actually comes because when you excite an electron, then you change the system. And because the effective potentials, like the self-energy or the Hartree potential, depend on the system, they depend on the density and they depend on the Green's function, this change gives you an effective interaction. And this is what I have written here. So my electrons and holes that do not interact get an effective interaction from the change of the potentials. And this is the Bethe-Salpeter equation. And if we use the GW approximation, then we can calculate this change, we can calculate this effective interaction, and we get a bare Coulomb interaction that is the change of the Hartree potential and a screened Coulomb interaction, an attractive screened Coulomb interaction from the GW self-energy. Okay, so now you can again see this Dyson equation. Again, it's again a sort of Dyson equation. It represents a new auxiliary system, and this time we have an effective interaction instead of an effective potential. But the principle is right the same. Okay, and calculations in this framework have been done for a long time, even before the 80s, in a semi-empirical way, and then we have all the ab initio calculations that came later. And of course, if I show it to you, because it works well. So Vitali solved the Bethe-Salpeter equation for this material, and the result is the blue curve. So we have a huge redshift and big intensity at the onset. And on the right side, you can see very nice agreement with experiment. And doing calculations not only allows you to reproduce experiment, it allows you to analyze experiment. And you can see that, for example, you can say, suppose I put my hole somewhere, where does the electron go? And in these pictures, you have this bright exciton where you have the strong peak here. Vitali has put the hole on a bridge oxygen, and the yellow is the distribution of the electron. And you can see the electron goes quite far away, in spite of the fact that this is a very strongly bound exciton. And this tells you another thing. It tells you that textbook models that would tell you, for example, as soon as you have a strongly bound exciton, the electron is very close to the hole, should be taken with care. Here we have complex materials, and here you can really see what ab initio calculations can give you beyond these textbook models. Another sort of thing beyond textbook models is excitons in metals. Okay, you would think that what the hell should this be? And here I gave as a title for the slide, a search for ghosts. And this is work by Jaco and Matteo and myself. And we will look first at this graph. So we have an inverse dielectric function here, actually a static. So it's a static screening, okay, as a function of wave vector. So static screening is what usually decreases your Coulomb interaction, okay? And what you can see here in this black curve, which is labeled COPD, which is actually a fit to a Monte Carlo calculation, so it should be exact, in a low density gas, RS equals 6, is that this screening can become negative. So in this range here, you have actually negative screening, which people have found sometimes quite astonishing. And they have explained that this is due to the fact that we start to build up low energy modes in the system at low density, and in the irreducible polarizability, which is the response to a total classical field, you even get imaginary poles. So your excitation energies, let's say, move to 0 and then go on the imaginary axis, and this then gives rise to negative screening. And actually, the homogeneous electron gas at low density has a very complex sort of diagram with a lot of excitations that you wouldn't even suspect, among which these ghost excitons. And I will not go into this, but if you're interested, I took this picture from Takada. And this is a picture actually at RS equal 22, so a very low density gas. And why I show this to you is when, well, we said, is this really, can we really say this is an exciton, okay? If it's an exciton, it shouldn't be there in the RPA. So Jaco did an RPA calculation, it's the green curve, and indeed, there is no negative screening. But then it should be there in the beta salpeter calculation. So we did a beta salpeter calculation in our usual approximations. And you see, it goes a little bit down, but there's no trace of negative screening. Curiosity, if you do an adiabatic local density approximation calculation, you are almost on top of the quantum Monte Carlo. Okay, so the beta salpeter result is actually lousy in the low density homogeneous electron gas in our approximations. And you can say, why should there be an exciton? Well, it can only be because we think there shouldn't be an exciton, because we think that the metal is so strongly screening that there cannot be an electron-hole interaction. But the screening is actually not complete even in a metal. First, because of retardation. So if you start to screen, it takes time to build up the screening cloud. And one of the approximations we always do is we think that interactions are instantaneous in the electron-hole problem. And that's, of course, wrong. It's not instantaneous. So this could explain less screening. Second reason, at short distances, even in a metal, screening is incomplete. And this is particularly important when you think that what we really screen in our system are not classical charges. It should be the screening of fermions. And this allows us actually to go beyond this GW picture and to build what is called vertex correction. So vertex corrections go beyond GW. And when you do this, when you go in the beta salpeter equation beyond the GW level, you start to see the good tendencies. And if you're interested, we can discuss this later, but I will not do this now because it will be too late otherwise. So you can see that in Green's functional theory, you have the same concepts as in DFT. You have a quite compact object, the Green's function, that describes your system. It's a little less compact than the density. And you have an auxiliary system. And because it's less compact than the density, Green's function gives you more observables in a simple way. You have more exact functionals for observables, in particular photo emission. It's computationally, of course, more demanding, especially if you go to two-body problems like the electron-hole problem. And you can see there's a sort of compromise between the full wave function and the density. And perturbation theory is actually very successfully used, and it's perturbation theory in the Coulomb interaction. But sometimes the first order is not enough, as in the problem I have just shown you. The exciton in the homogeneous electron gas or in any metal is not enough to stay on this level. And then it gets quickly very, very complicated. When first order perturbation theory is not enough, then we are really into trouble and it's hard to do much better. And therefore, I think that we have to think about approximation strategies other than perturbation theory. So the things I would propose you for discussion are 5 things, and we can maybe choose later. So it's to talk about auxiliary systems which have the same sort of similar observables accessible as the self-energies, but that are local, so that we can use locality. DMFT, dynamical mean field theory, is actually an example that I would be delighted to show you if you're interested. We have other local spectral potentials that we can talk about. We have also ideas of how we can move away from perturbation theory and really use model systems, like in the case of the local density approximation, in a systematic way. And we can also see whether the fact that our self-energy depends on 2 space variables cannot be used in terms of sum by locality. And I will actually ask Ignacio how much time I have now.
You still have, say, eight minutes left.
8 minutes. Okay, then I will just start with my list, because I think it's would be nice to go at least to a DMFT. Okay. So the comparison between density functional theory and Green's functional theory is here. So in density functional theory, we have the density that describes our system, and we have an auxiliary potential in the Kunsham system that is local and static. And in Green's functional theory, our descriptor, let's say, is a one-body Green's function, for example. It is non-local in space, and it is frequency dependent. By the way, it's also non-local in spin. I have not gone into this here. And the auxiliary potential-like object is, by consequence, also non-local in space and frequency dependent. But we can still say, can we learn from DFT? Because in DFT, usually we don't do perturbation theory, right? So can we learn from the approximations that DFT people have developed? And can we do something like a local density approximation for the self-energy, or local Green's functional approximation? Okay. First, we can realize that very often we are actually not interested in the full Green's function either. Exactly in the same way that we are not interested in the full many-body wave function. We are interested in observables that are integrals. And in the case of spectroscopy, very often we are actually interested in a spectral function that is the trace of our individual spectral functions. The trace, which is invariant. So we can write it in any basis. So for example, the sum over all wave vectors would be the same as the integral over the diagonal in real space. And here you can maybe already see where I will come to. So it's actually enough to have the diagonal of the one-body Green's function if you want to have the integrated spectral function. And this is again local. There's only one point here, and therefore we can build an auxiliary system that is local in space. It's still frequency dependent because we have a frequency dependence here. And we have shown this many years ago, actually, that you can build such an auxiliary system that is much easier. And this will, of course, now allow you to talk about locality as in the case of the Kunsham system. And people who do this really are the people from dynamical mean field theory. So they wouldn't maybe present you things in this way, but I think it's interesting to do it. So as I said, the trace is invariant. We can go in any basis. So the basis that dynamical mean field theory would typically work in is orbital space. And here this L actually stands for atomic sites. Then you have other arguments here that I have not shown, like orbitals, okay? But these are atomic sites. And so we take the diagonal on atomic site, and which has a certain degree of locality, of course, if you are limited to one atom. And for such a Green's function, for such a diagonal element, it is actually enough to have an auxiliary system with a local self-energy, which is local in this site basis. So it just lives on one site. So we can again talk about locality, and we can do something like a local density approximation, the analogous, much more sophisticated, of course. Okay, so we can see the analogy: a local local self-energy, like a local potential, and a local Green's function that would be the object that you get from this auxiliary system. Now, the principle is the same. You have a material, and at every point, at every site, you will use the result of a model. Only that in DMFT, the model is the Anderson impurity model. So it's an impurity that is surrounded by some effective medium. Okay, and in the case of DFT, you say that you take your model at the same local density as your material. By analogy, in DMFT, you take your Anderson impurity model in the way that it has the same local spectral function as your material. But the thing is strictly analogous. And you see, again, this nearsightedness, and this nearsightedness actually appears and can be used because you think that there's an approximation that your local self-energy depends only on the local Green's function, like in the case of the LDA, your exchange correlation potential in a point depends only on the local density. Okay, so this nearsightedness turns out to be a very good approximation for many of these strongly correlated materials that actually have very localized electrons. And therefore, this local approximation works very well. And as you know, DMFT has had a big success. And I think I will maybe stop here. So you can carry this much further, and I could talk to you, for example, about having locality really in real space here with our spectral potentials. But I will leave this for the discussion if you are interested. And I would simply make a sort of advertisement for the use of models here. Because this strategy to replace unknowns in a material by a model has, of course, a really, really big advantage. As we have seen in the LDA, in principle, it allows you to calculate your model series once and forever, to store it and to share the results. And this is a gain in efficiency, which is really, really, really huge. And so this is something that you cannot do with perturbation theory, because your perturbation theory, in a way, also uses the model. A model can be the starting point of perturbation theory. In the case of many-body perturbation theory, this would just be the non-interacting system. But the non-interacting system is too system specific. It's different for every material. So it's very difficult to make this collection of results. Okay, but this could be really, really great. Okay, so models can be used in different ways as starting point for perturbation theory. We could optimize them variationally. They can replace a quantity in the real material locally, and I put this in quotation marks because locality can be locality in real space, can be locality in site basis. It could also be locality in some configuration space other than real space. And in this way can lead to incredibly efficient calculations. See the example of the LDA, which made density functional theory possible. Okay, so I think that I would like to conclude with this. The winning strategies is something we really have to discuss about instead of simply carrying on what we are doing. And the only thing that I would also like to conclude is about the importance of the collective effects. And so I would say that the future is definitely collective and should be determined by us wanting to share. And that's what we're doing here. Thank you for your attention.
Thank you, Lucia, for this very insightful presentation. So I think now we have the time for the discussion. I remind you that you can indicate simply that you want to ask a question through the question and answer channel, the Q&A. You simply indicate your interest to ask a question, and then we will unmute you, and then you can directly talk with Lucia on whatever you want to pick it up from this thorough discussion about how to go beyond DFT and capture different effects in the dynamics and the dynamic properties of these materials.
You want me to stop sharing, or?
Yeah, maybe there is no, I mean, I don't know, depending on the questions, you can always share back, but maybe there is no need to carry out questions with this. So while we wait, so I mean, thank you. I think it was very nice to see this overview. So I had a curiosity when you have talked at the very end about this dynamical mean field. So in a way, you have been talking about this short-sightedness, or the locality, non-locality, the when this is important or not. At the end, I mean, the way you were showing it, it looked to me as if it suggests that when you start having, you have these correlations of two-body effects, is the non-locality in time that really matters. Is this frequency more than the K or space dependence? Is this something specific of this type of quantity you were focused on, or there is a particular reason why you think this dynamic mean field is more insightful or captures more the essence of these correlations?
Okay, so that's several important points, actually. Okay, so one is the non-locality in time. You are right. This is, I think, very, very important for any kind of spectroscopy. As soon as you have any kind of coupling effects that you want to see, like the satellites I've shown you. And actually, if you think of the materials where dynamical mean field theory is particularly successful, these are materials where the satellites gain actually more importance than the quasi-particle, okay? So they move away from this band picture. Okay. So it's very strong coupling. And these are things where you really need time, yeah? You build up excitations in time, so the frequency dependence is super important. Okay, and then you can, of course, say, how do I get it? In principle, you get it with any frequency dependent self energy. And now you have to design a good approximation, but you need really frequency dependence, okay? In a direct or implicit way. Even for so-called weakly correlated system, and this is why I showed aluminum, this is not strongly correlated, but if you're interested in these additional features, in these satellites, in everything that comes from coupling that you cannot capture with a one electron picture, you need frequency dependence.
You would say it's the basic fundamental ingredient beyond.
Yeah, yes. So this must be in your auxiliary system. Okay.
Okay. So there is now a question by Domenico Corona. So you can ask the question yourself. No? Domenico? No? He maybe has problems to get the mic on. Right, so I asked the question, and then if he can have access to the mic, maybe he can build on it. He asks, in which aspects Bethe-Salpeter is better than the time-dependent DFT?
Okay, so first of all, in principle, exact Bethe-Salpeter and exact TD-DFT would give you the same spectra. And this is because we are talking about spectra of neutral excitations. Okay, so Bethe-Salpeter is a linear response equation that gives you in principle the exact linear response spectrum, and you can do TD-DFT in linear response, and then it gives you in principle the same. Now, TD-DFT is more than linear response, so you can also go beyond nonlinear response, beyond linear response. You can go to real-time propagation and all that. Bethe-Salpeter is by itself, because it's a Dyson-like equation, is linear response, but you can generalize it to time-dependent Green's functional theory. Okay, like you do time-dependent density functional theory, you can do time-dependent Green's functional theory, and Bethe-Salpeter would be the linear response part. Then comes the question, and this is really very fundamental, because I said in the beginning, we will not solve the many-body problem exactly. And I can tell you, we will not find the exact Bethe-Salpeter equation. We will not find the exact TD-DFT. So the question is only, for which one can we find better approximations? Okay, This is the question. And this depends a little bit on the situation, because in general, we think that beta salpeter gives better results. In general, it does. It's more costly, gives better results. But I have shown you the metal on purpose because it's an example where it's worse. Okay, so don't sleep.
Okay. Yeah, nice. So there is now a question by Francesco Sottile. So you have to mute yourself. So we.
Yes. Can you hear me? Yes.
Yes, we can hear you.
Since you started from comparison with density functional theory, in which we have now a lot of constraints known about the density and the theorem. We have a lot of sum rules. So we have a lot of mathematical aspects that are quite advanced, both for the ground state and also for the time-dependent case. And I have the impression that we have much less for the functional of the Green's functions.
Okay.
Now,
yeah.
So my question is not about, because I'm particularly fond of the mathematical aspects, but like uniqueness or the convergency, but sometimes I have the impression that can have a very practical consequences. For example, when you have non-linear equations like the quasi-particle, so you can have multiple solutions. So there are some important practical points, right?
That is right. Actually, something that I would really like to stress is I try to talk about more than one method in one single seminar, which is bad practice in principle. But I think that we absolutely have to compare methods because we have to learn from each other. And in particular, we can learn a lot from DFT, we Green's function people, and the DFT people, as you point out, they use, for example, to find their functionals, they use a lot of exact constraints. And I think we should do the same. And it's not true that we don't know them. So we know a lot of exact constraints also in the case of Green's functions, like word identities, sum rules, okay? But we don't use them enough because we have gone perturbation theory. It sounds great. It looks so systematic, okay? And then we always stopped at first order and we didn't worry. We have to use the exact constraints, for example. The other point is, of course, okay, in density functional theory, people have spent some time to say, what is a good density? I mean, a good density, it's a density that you can obtain in principle by solving the many-body Schrödinger equation of a system with a local potential. This is what we want. And it turns out that essentially most of the densities are legitimate. It's enough that they be positive, for example. That's very important. That's very simple. If you ask what is a good Green's function, so if you want to constrain your system such that it has a Green's function that you could calculate in principle from a many-body system with a local potential, you will find that most of the Green's functions, most of the objects that are functions of two space variable and a frequency are not legitimate Green's functions. And these constraints, besides the fact that they must be a sum over poles, these are much less known. And here we have really difficulties to constrain this. And if you want to do propagations and solve differential equations and design approximations, this would be really nice if we knew more.
Okay, thank you. So now there is a question by Eugene Ruskan. You can mute yourself.
Hello, I have a question on the software you're using for these Green functions and and what kind of computational time comparison you have with the DFT versions of these code and scalability with the system size.
Okay, of course, it depends which code you're using. You're saying this. So we in the group, and maybe Francesco wants to say more about it, because actually Francesco has been asking his question from the next office and he's responsible for our codes, okay? We in the group are developers. And so the important thing of our codes is that you can put your hands inside and develop them, okay? It's not to be fast. And so we have the sort of straightforward implementation. And this means that we typically scale with at least n to the 4th, okay? Beta salpeter, even worse, n to the 5th or n to the 6th, okay? But you can do better. Other groups do better. Groups that are specialized in being fast, doing applications with this kind of methods, right? So if you want numbers, maybe Francesco is here and wants to answer.
So we can also allow Francesco to speak. So if he wants to unmute himself and contribute.
Well, I can confirm in terms of the scaling and the approach. I do not have a precise comparison with DMFT in particular, but yes, for what concern in general density functional approach to obtain, for example, a band gap, a Kunsham band gap, and obtaining the same thing with the Green's function formalism, for example, in the GW, the difference will depend strongly on the system, but we can easily talk about doing a calculation of, let's say, an hour for the Kunsham, even if it is a very complicated material, and it will be in the order of, let's say, several hours if you want to do it for, let's say, with the GW approximation. Very often it is much less if you have just 1 or 2 atoms per cell. Yeah, the n cube n fourth for the DFT and GW respectively is okay, is what we have normally. And so this can explode easily, increasing the number of electrons.
But we should really say that there are much more efficient approaches out there now. I mean, I don't want to, it's a little arbitrary what I say now, but for example, if you look at the stochastic approaches, where you have stochastic approaches to spectroscopy, you calculate a lot of integrals using stochastic methods, and you can speed up a lot, because instead of, let's say, roughly speaking, instead of summing over your orbital basis, which has a number that scales as it scales, you sum over stochastic numbers, and then you always have the same number, okay, roughly speaking. So you can really get the scaling down by clever methods, by clever basis sets also for the response function. There are a lot of possibilities. And so if you are heading for really optimized code, you can do better. And people do calculate hundreds of atoms and do spectroscopy with Green's functions. Huh?
Okay. Thank you for this collective response. Now we can move to the next question. That's by Nicolas Tancogne. So you can unmute yourself and ask the question.
Okay, thanks. So I have a question, or more say a curiosity, on the frequency dependence of the Green's function self-energy. So in density functional theory, we know many things about, for example, spatial dependence. And for the Green's functions is also true, but what do we know exactly for the frequency dependence? Say, do we have some, I don't know, near-sightedness principle or some exact sum rules that tell us a bit more about how we behave in frequency space? And how much of this is transferable to, say, different systems? Because usually it seemed to me that any systems has quite generic spatial properties, but the frequency dependence seems to be very dependent on if you have a plasmon or if I have any other mode that's collective excitations, let's say.
Yeah.
And, yeah. So, and also if, I have the feeling that depending if you do DMFT with a local self-energy or if you do GW with non-local self-energy, the frequency component is sort of shift to the spatial non-locality sometimes. So
okay, these are a lot of questions.
Yes, I am sorry.
Let me start at the end, and you say what I forgot. Okay.
Okay.
So the last question is yes. So non-locality and frequency dependence are to some extent interchangeable. And you can maybe understand this in physics reason, because you can imagine that frequency dependence brings you additional excitations and they can represent complicated correlation effects, okay? But you could represent them as sort of additional non-interacting particles that make their own excitations, right? And then it becomes non-local. You can also see it mathematically. If you want to have a given spectrum, you can obtain it by a non-local static operator if you have enough spatial degrees of freedom, or by a local frequency-dependent operator if you have enough freedom on the frequency. You can obtain exactly the same spectrum. You can write down this mathematically. So they're interchangeable, okay? And this means that you have to be very careful when you interpret that stuff, right? The nice thing of many-body perturbation theory, I must say, is that we have a very good interpretation of what all these frequency dependence means, because as I've shown you, we write this, perturbation expansion is actually an expansion in processes where you see the excitations, so you immediately see what it is. And then you asked of what we know in principle. So of course there are some rules, okay? If you take the easiest one, you integrate the spectral function, you get the density, okay? So that is the easiest sum rule. And then you have all the moments and you get more sum rules. Another thing, you know that a respectable Green's function must be a sum over poles. So you know the in principle structure of your Green's function, okay? Then you might also ask the question, how much detail do we need? And that's also an important question, because if you take, for example, the GW approximation, it contains W, and W contains in principle all neutral excitations of the system, okay, charge excitations. And but if you look at what is really important, you look at the spectrum of this excitations. W is screened by the inverse dielectric function. The inverse dielectric function is dominated in simple materials, simple semiconductors, metals, and so on, by the plasmon. So essentially you see the plasmon, and all the other excitations that make us so much trouble in absorption, you essentially don't see them. So so that's where you can simplify. And now I don't remember whether you asked me something else.
Oh, that's more or less it. Oh, thanks a lot, Lucia.
Okay, you're welcome.
Thank you very much. So now John Rare also has a question. You can unmute yourself. John.
Okay, can you hear me?
Yes.
Sure.
Okay, hi, Lucia.
Hi.
So thinking about your talk, I'm wondering whether it's possible to build in variational properties in the functionals. I mean, some functionals are better than others because they have some sort of variational property, like in the energy or something like that, which is what Hohenberg and Kohn did with DFT. It's why the density functional has a lot of nice properties. So what do you think?
Yes, this is true. I mean, there are many different ways to come to the same result, actually. So if we start with the Green's functions, the self-energy per se, you can write it in a very analogous way to DFT with functionals and with a variational functional. So instead of writing the total energy with the Galitzky-Migdal formula, which is not variational, so okay, you can write the energy as a functional of the Green's function with a thing where you can make use of a variational property, okay? Really analogous to DFT. And the only difference is that you can have a saddle point. You don't necessarily get a minimum when your derivative is 0, okay? So that makes it, of course, more complicated. I think this may be linked to the fact that we don't know enough how to constrain our Green's functions, okay? So if you allow me to search all possible Green's functions, I would actually be in trouble because I wouldn't know how to tell you what are all possible Green's functions, okay? Another thing is that, for example, if you take dynamical mean field theory, so the way I have presented it to you is not the way it's usually presented. And I have presented it to you as an analogy to LDA, simply more evolved, more sophisticated, but you can also derive it from a variational approach. And you can see it as a sort of optimization of the use of this model to give you the real system. Okay, you can say, I want to use a model, in this case, the Anderson impurity model, to represent my system and to get my local Green's function, and I optimize this model. And this is a variational procedure, actually. So you can do a lot of things variationally. Now, this, of course, supposes that you have an energy functional from which you can derive your self-energy. Like in the case of DFT, you have the exchange correlation energy from which you can derive your exchange correlation potential, right? And as you know, not all self-energies that we use can be derived from an energy, meaning that we are making approximations where the self-energy is actually not the functional derivative of an energy functional. And you might think that this is completely terrible. And in fact, it does violate some rules. It's what we call not conserving. But it can turn out in practice that for the questions you're interested in, this gives a better approximation. So yeah, the variational approach is super useful in principle. Okay, it allows you to derive the equations that I have shown you. It can also help you to get good approximations, but it can also be, if you use it in a more Taliban-like way, hinder you to find good approximations for things you're interested in.
Okay, hey, thanks.
Yeah, thank you very much. I have now a question by Jack Wetherill.
Yeah, so in one of your figures, you showed us the GW plus cumulant method being applied to a real system, and it gave a very good band structure. And then there was this mysteriously labeled cumulant plus plus that included some extra features that gave an extremely good band structure. Could you go into a few details of what was added to the cumulant method?
Yeah, let me come back and then I will share my screen. Okay. So, can you see that?
Yes.
Okay, super. So you're referring to the right panel, and it's good that John Rare has just been talking, because he's a main player in this, and you can see his name here as well as Josh Cass. So the fact is that when we compare theory and experiment, not everything that is difficult is correlation. Okay, very often we don't measure what we calculate, and we don't calculate what we think we measure. And if you take, for example, photo emission, I told you that the spectral function is what we measure, but this was a lie. Okay, the spectral function, as I have defined it, is the removal of the electron from the n-electron system. But once we have taken this electron, okay, what we measure is the electron at the detector. So the electron has to go through the material, through the surface, and fly to the detector. This is what we measure, okay? And so, for example, when the electron goes through the material to come to the detector, it can scatter. It will again meet other electrons, and it will again, for example, emit plasmons. And so it will again lose energy. And when you then come to the detector, you will find that you have more electrons that have plasmon satellites, right? Because you have reinforced the plasmons. And you can see on the right panel that this first plasmon satellite is much stronger than in the intrinsic spectral function that we calculated. And this is not because we calculated wrongly the spectral function. It's because what we measure is the spectral function plus the plasmons that have been created by the outgoing electron. And this is what is called in photo emission extrinsic effects. And then we have interference between the two. And on this, we have been collaborating with John and Josh. And it was mainly actually Josh and John who have been working on this, and to add these effects to our spectrum. And then there are other effects here. This is just an example. Another effect is that this was an experiment at 35 Kelvin, and aluminum, even at 35 Kelvin, is not to be considered at 0 Kelvin. You still have the effect of the moving ions, and this means that you destroy some of the momentum resolution and you get non-dispersing features, which you can actually see, especially in the band structure region. See this green here, which is in the experiment. It's not in the intrinsic spectral function. At the Fermi level, you shouldn't have anything here. but you have it. And this comes because the ions move, and we have also included this. And then we have included, of course, matrix elements effect. And so there are a lot of things in the experiment that you have to and can include if you want to have really good agreement.
And so this difference between what you think you measure and what you do measure, you've mentioned the scattering effects and temperature effects. Do you also have to include relativistic effects, which of course wouldn't be included if you solve the time-dependent Schrödinger equation exactly in this case?
Well, we could also include relativistic effects, yeah, for example. Okay, there are a lot of things you can do. And then the question is, how important are they, right?
Yeah,
I mean, of course, if
you
you have really heavy elements, then you, even in your band structure calculations, you put relativistic effects. Then, of course, you have, since you're talking about maybe the photon, you can have the fact that we do the dipole approximation for the excitation, right? And according to the X-ray you are using, maybe you want to go beyond that. So that's another possibility.
Okay, thank you very much. Now we have another question by Massimo Altarelli. He had written it down in the Q&A, but if you mute yourself, you can ask it directly to Lucia.
Well, yes, I was, trying to make sense of your beautiful description of the, the progression in complication of systems and what you need to apply. And I somehow got the impression that you emphasized that this short-sighted, when short-sightedness fails, this is the main reason of failure of LDA. But, there is this simple example, the most simple case of a strongly correlated system is an atom with an incomplete shell. Yeah, then you know that, well, in an atom, you are short-sighted, you see all that there is to see. But the problem is that that thing is intrinsically badly described by a single Slater determinant that gives you the trouble, right?
Absolutely, yeah.
And this is also something that you find then, in the problems that have justified the invention of the MFT, like, all this Hubbard model, millions of papers on Hubbard models. There, the problem is in the Hubbard model, with one Slater determinant, you don't go very far. Isn't that another way to look at this?
Absolutely. In fact, I have left out a whole chapter of all this story. In fact, I didn't want to say that the nearsightedness, this approximation of nearsightedness is the only problem here, okay? You mentioned this other problem of degeneracy, let's say, generally speaking, degeneracy. And degeneracy, you can, for example, immediately understand that when your system starts to be degenerate, straightforward perturbation theory has a problem, right? You have to do something that takes into account this degeneracy, which means, for example, more than one Slater determinant. Absolutely clear. Now, in principle, if you believe that a DFT is in principle exact, of course, you could say, if I manage to build the correct functional, then I could still describe all that. And it turns out, for example, for a very strongly correlated system, you would be in the situation that the Kunsham gap, the exact Kunsham gap of a strongly correlated insulator would be 0, completely different from what you measure, okay, because it's an insulator. But this is just because you look at the Kunsham system. So that's still another problem, okay? So you could do the really exact DFT, and you would still have a 0 band gap in the Kunsham system. And this is very important, because often in this discussion with DMFT, people compare the Kunsham spectrum to the experiment and draw conclusions about correlation, but this is not correct. But I completely agree with you. The story of degeneracy, like in an open shell atom, this is another story, and that merits a long discussion of how should we approach that. That is clear. One way could be, for example, symmetry breaking and symmetry restorage along the lines of Gustavo, how you call it, Scuseria, and so on. But okay, there are many possibilities.
Okay.
Yeah.
Thank you very much.
Thank you very much. I don't see any additional question. I think we
Can I maybe ask one?
Yes, Sarah, please.
Hi, Lucia. I was intrigued by your ode to models at the end in two ways, and I was wondering if you could comment on that. The first one is that, of course, there is a certain art into choosing the model for each specific situation, and so I was wondering if you have, any general comment on that. If you think that then this is something that goes against the notion of systematizing the way in which we approach these sort of problems, and if systematization is a virtue, maybe not necessarily. And then, is there a feedback mechanism? I mean, once you have identified a model, can you use that model to maybe go back to something like, a perturbation approach, and then understand better what are the terms that you're not allowed to drop?
Yes. So let me again look for some slide. Okay. Okay, so before we talk about the slide, let me say that the choice of the model actually is much more complicated than one would have thought, because you can have different criteria, and this also depends on what you want to do. So, for example, we in Palaiseau, what we would like to do is to build on the success of the LDA, not only in the context of DFT, but for all kind of applications, observables, theories, and say, could we have a model, or to be precise, a series of models, because the LDA is a series of homogeneous electron gases, okay, that we could calculate, where we could interpolate the results, that we could store and then share, such that the model doesn't have to be recalculated again. Because there's one thing I didn't point out in the comparison of LDA and DMFT. In the DMFT, the Anderson impurity model is recalculated every time people do a DMFT calculation. So they do not profit from what the LDA profits from, the fact that the model has already been calculated. So I think one criterion, and at the end one has to make a trade-off, is, can I calculate this model once and forever, and can I store it, and can I share the results such that we can use it over and over again? This would be the big gain. The second criterion would be, the model must be reasonably universal, in the sense that you could use it for a wide class of materials. The homogeneous electron gas is very universal. You can use it for every solid. This you can easily understand, okay? But it's even used for atoms, molecules. It's incredible. And this has probably very deep reasons, which I have been discussing also with Hardy Gross and with Kieron Burke, and which might be really linked to other features, to expansions in H-bar, and really things you don't think about, okay? So this is one. And then, of course, the most obvious thing is that the more your model contains the essential physics that you want to find in your material, the more it is useful immediately, right? So the optimization of the model is, of course, an important thing. And I put this slide because it's an example on something we are working on, and which we call connector theory. And you can find it in this reference down here, especially the second one. It's actually, I didn't put the exact reference, but it has come out in the meantime, so it's published. And it's about going beyond the LDA by saying, okay, I want, for example, it's just an example, the exchange correlation potential in a point is a function of the density. I postulate that I could obtain it from the homogeneous electron gas, taken at a homogeneous density, which I don't know, but I suppose it exists. And then the question is, how can I find this density? And this is exactly your question, right? How can I tune my model such that it's really optimal? And in the LDA, you just use this intuition of nearsightedness, which might break down, of course. And if the system is not so nearsighted, you need a sort of systematic way to make this approximation better. So the choice of this optimal homogeneous density. And this is what we call connector theory, strategy to optimize this homogeneous density. Okay. And this you can do it in principle also with other models. It's simply more complicated because the nice thing of the homogeneous electron gas is also depends only on one parameter, namely the homogeneous density. As soon as you go to more sophisticated models, you have many more parameters, and then you have to optimize and you have to choose which is the most important one, and that makes it much more complicated. And we're actually working on this. And another thing is maybe also interesting. It's the consideration that I told you that when we are not local but non-local in space, we cannot use the nearsightedness anymore. But it actually turns out, for example, if you look at the density matrix, and Jack, who was asking a question earlier, knows this very well. Many density matrices in point R1 and R2 are essentially determined by the density in point 1 and point 2. So it's sort of double nearsighted. And so we would need a model that is inhomogeneous and has the density in point 1 has density 1 and in point 2 has density 2. So we could also generalize it in this way. But all this is actually work in progress. So there are many open questions.
Thank you.
Thank you very much. I think we have had a very nice and wide discussion. There is the second part for the register and gather, where there is the possibility to follow up this more informally if you want. So I think now we can move to the, so thank you, Lucia, again. We can move to the second speaker of this first part. So today is Jean-Baptiste Van Kam from the University of Yaoundé. We'll be talking about theoretical investigation of the structure and properties of particular molecular compounds. So Jean-Baptiste, you can now unmute yourself and the floor is yours.
Thank Professor to give me the floor. Yeah, can you see my screen?
Yeah, we see it. Remember to speak a bit loud so that we can, yes, yeah, perfect.
Okay, great. As I was saying, thanks for giving me the floor. My name is Jean-Baptiste Van Kam, a young PhD holder in computational material science at the University of Yaoundé 1, Cameroon. My topic today is about the theoretical investigation of the molecular structure, vibrational spectra, thermodynamic and nonlinear optical properties of 4,5-dibromo, 2,7-dinitro-fluorescein. During my speech, I will talk about the geometric parameter which contain dipole moment, average probability, related anisotropy, first molecular hyperbolizability. Also, for the thermodynamic properties, we will talk about the zero-point vibrational energy, enthalpy, free gift energy, molar head capacity at the constant volume, entropy. Also, we talk about the nonlinear optical property of this compound. So, as an introduction, our compound, also called eosin B dye, is an organic dye, mostly used in many subjects like medicinal, food, or in medicine, we use it as an antimalarial drug. Now, the objective of our study is to numerically determine the molecular structure, electric parameter, optoelectronic properties of this compound. Also, we have used many methods. Yes, as this second part of our slide, talking about material and method. For the method, we have used ab initio as a restricted artifact. Also, For the density functional theory, we have used many hybrid functional like PBE1, PBE, also called PB0 in the literature. We have used MPW1, PW91. We have used B3LIP. Also, we have used B3PW91 with the CC PVDZ basis set, which is the Jennings correlation consistent valence polarized double zeta. A basis set is a mathematical function used to describe the electron distribution. As material, we are used the gas as environment because we don't use solvent media here. We have used a Windows version of Gaussian to simulate our compound. Also, we have used the Microsoft Office to analyze our data. But for the full article, we have used also Python to draw our graph. As you can see here in the figure 1, you can see our compound that we draw with Gauss view. We do our input file with Gauss view also, and we optimize our compound. So at the beginning, we use the semi-empirical method to pre-optimize our compound. After, we use the restricted artifact to optimize our compound. At the end, we use the density functional theory to affine our structure. So after the optimization, to see if our compound has reached the local minimum, we also compute the frequency calculation to see if our compound is stable. And to do that, we analyze the frequency. All our frequency was positive. That means that our compound is stable. If it has a negative frequency, that means that our compound is not stable. So as our compound is stable, we can continue with our calculation. Here we did the electric parameter. You can see here some formula. 1 is the dipole moment. The 2 is the average probability. The 3 is the first hyperbolability. The 4th is the anisotropy. So here in the table 1, you can see some parameter that we have calculated. Here we can, the most important thing is about the dipole moment and the first molecular hyperbolability. Which one? These two parameters is very important to compare our property to see if our property can be used as a non-linear optical properties. So to do this, we used to compare our result with urea. Urea is a prototype molecule used for the purpose of comparison of the study of nonlinear properties. So our compound has the medicinal use, so we can use the urea to do the comparison. After that, we noticed that these two parameters, the dipole moment and the first molecular hyperbolability, is very high than urea. So we can conclude that our compound can be used as a non-linear optical properties. Also, we have calculated the thermodynamic properties, which contain the zero point vibrational energy, the free Gibbs energy, the enthalpy, the entropy, and more other. And this table 2, you can see here the parameter that we have used. We have used many methods. Why? Because we don't have the experimental values. So we have used many methods to see which one can be best used for the future study. Also, we can see here the entropy is very high at B3LIP. Also, the electronic energy is very low at B3LIP. So we can say that this B3LIP can be best describe our property for the further study. We can see down for the figure 2, the HOMO and LUMO orbital. The first one is the HOMO. The HOMO is the high occupied molecular orbitals, and the second is the LUMO, which is the lowest in occupied molecular orbital. These two is these two orbitals is these two parameters, HOMO and LUMO. You can use it to have the band gap energy. Here, this figure 3 concern the variation, how the band gap energy move. You can see here with the restricted artifact. Here you can see the DFT method. So we can notice that with the restricted artifact, the band gap energy is very high. It's above 8 electron volt. And now for the density functional theory, you can see that it's around 4 or 4 electron volt or less. We can see here the optoelectronic properties that we use to model describe our compound. We can see here we reduce the volume. Here you can see the electric field, the pulsability, the geometry constant, the refractive index, also the displacement vector. Here you can see the band gap energy. You can see here with the restricted artifact, the band gap energy is greater than 8, and with the DFT is around 4 or less. So actually we have the many property, but here we just give some interesting one. So as conclusion, we can notice that our band gap energy is around 3.78 and 4.22 electron volt. That means that with the correlation energy, with the correlation of electron, the band gap energy is reducing. Why? When you don't use the correlation effect of the effect of correlation, the band gap increase. Also, with this energy, we can say that the compound can be visible in radiation and infrared at temperature. Also, we can see that with this band gap energy, the lowest energy can be found at B3 lip. Also, we can say that our compound can be used as a dense sensitized solar cells. As we use the thermodynamic properties to see if our compound is stable or not. Also, we can say that with B3 lip, our compound is stable and has the lowest energy, electronic energy, and is less stable when we have the restricted artifact. Also, the correlation effect of electron shows us that the band gap energy decrease with this effect. Our compound also has attractive property for nonlinear optical properties. So when we do the comparison with urea is a compound that we usually use to compare the compound which has medicinal properties. Also to see if this compound can be used for nonlinear optical properties. Also, our compound confirmed that we can use this compound eosin dye as a medicinal and also as a optoelectronic properties. Also, we can see that at the last point, the B3 lip and PW1, PW91 are best hybrid functional that we can use for the further study. Also, for our further study, we have used this B3 lip and restricted artifact. Also, we have used the solvent media because our compound have the medicinal use, so we need to see how our compound can be useful in that subject. And also, when we do this study, we see that this compound can be used as an antimalarial and coronavirus drug. So this compound is more interesting. For acknowledgement, you can see here that we are thankful to the Council of Scientific and Industrial Research, India, that give through Professor Emeritus A.N. Singh, which is the professor of Department of Biomass University in India, who purchased the Gosha software and give the software to one of my supervisor, Professor Gavison Eju, will give the software to me so that I can run my calculation. So here you can see some references that we use to do our computation. So this is the end of my talk. Thanks for your kind attention.
Okay, thank you very much, Jean-Baptiste, for the presentation. We have now the time for questions. So remember, it's enough that you indicate in the Q&A channel of Zoom your interest to ask a question, and then we can unmute you. I had a curiosity because at some point you were referring to the importance of understanding the behavior of this compound in water, but it's not clear to me. So you did already the same kind of a study with and without water to see how water was affecting the properties of this compound?
Yes, Prof, I did. And also I noticed that water is based on what we use water to take this compound, because when we use water, we see that this compound is more soluble in water. So we can use this compound with water to have to take our medicine. So the water is best used to drink this compound.
Mm-hmm. And also, as another curiosity, you mentioned that you didn't have experiments to compare with. There is none of the properties that you were discussing could be or had been studied for this particular compound?
No, for this particular compound, we also have the bound length. So we use the bound length to do the comparison. So we have only the bound length parameter, the experimental one. So we use it to do the comparison.
Okay.
But for the one, we're just trying to see where the compound is more stable or which one have the lowest electronic energy.
Mm-hmm. So then could you use, because you're using all these different methods, so you could compare then compare with experiments, at least for that quantity, which of these different methods works best?
We noticed that the B3 leap work best for this compound.
Yeah, that's the B3. Okay. Okay, I do not see any additional urgent question. So I think then we can finish this presentation. Thank you very much, Jean-Baptiste. And if you can stop sharing, thank you. I can just, so we come here to so I always like to show this slide saying thank you for attending, reminding you that both this presentation and all the lecture parts of the previous MixGen installments are available in our website and also through the CCAM channel in YouTube. And I also take the opportunity to remind you that if you want to keep updated on this type of events, on all other online events that we organize periodically, you can register and follow us on Twitter at CCAM Events.